Okay, welcome back for another exciting lesson on buffers. This is lesson 2, and today we're going to focus on the effects of adding strong acids and bases to solutions and various problem-solving strategies. First, I'm going to begin with a problem that's not in your notes so that we can kind of review what we covered in lesson 1. So, calculate the pH of a 0.5 liter of a buffer solution composed of 0.5 molar formic acid and 0.7 molar sodium formate. So we're not interested in the sodium. And then we're going to add 10 mils of 1 molar HCl. So this is a little bit different. So first we have to figure out what's going on. They want the pH before and after adding 10 mils of HCl. So we're going to calculate first what's going on between the formic acid, which is our acid, and the formate ion, which is our base. So the first thing that we have to know is so we have to know the Ka for formic acid. So Ka is equal to, and this is a formic acid, HCO2H, is equal to 1.8 times 10 to the minus 4. So let's look at what we have. We've got 0.5 and 0.7 for our molarities. They've given it to us. So we have significant quantities of our acid. So we have 0.5 molar of this. And then our formate ion, HCO2 minus, we have equal to 0.7 molar. So we have an acid-base pair, we have significant quantities, so we can do Henderson Hasselbalch. So pH is equal to pKa plus the log of the base over the acid. And so our pH is going to be equal to the negative log of 1.8 times 10 to the negative 4, which is going to give me 3.74 plus the log of my base, 0.7, divided by 0.5. And I get a pH equal to 3.89. So this is before. This is before. Now they're telling me that I'm going to add 10 mils of 1 molar HCl. When we do something like this, we basically have to respect molarity. So we need the concentration. We've got X over 0.01, which is going to give me, so that's going to give me 0.01 moles. Now, we have to digress a minute because I really want you to fully understand what's going on here. Originally, I told you that when you add acid, and this was in the last lesson, when you add acid, you've got X minus, you have some base, okay, and you're adding acid, so you're adding HX. In this case, you're adding acid, so that would be like your H3O plus, which is what we're doing in this case, except for we're adding it in the form of HCl, and we're going to produce more acid and OH minus. So it should make sense to you that as we add acid, as we increase the acid, that's going to make more collisions with the base, and the base is actually going to decrease because the two of them are working together to form more HX. So I want you to understand what's going on here. I'm going to use the original equation. So I'm going to use the pH equals pKa. Well, we actually calculated pKa. Using our equation that we just used, pH equals 3.74 plus the log of the base over the acid. Now, we have to think about what we're doing. I told you when we add acid, we're actually decreasing the base. So we need concentrations here. So our base, if you recall, was 0.7 molar. So your base is 0.7 molar. And if I was to set this up, molarity equals moles over liters. So I've got 0.7 equals x over 0.5. So if I were solving for x, it would be x equal to 0.7 times 0.5. Okay? Now remember, I'm adding acid, and I'm going to take away from the base. So I'm going to subtract, or 1 times 0.01. That's going to be my numerator. And my total volume, because I need a new volume, I had 0.5 liters when I had the original reaction, and now I have 10 mils, which is 0.01. So 0.5 plus 0.01 is going to give me a total of 0.51 liters. So this is over 0.51 liters. That's my base. Now for my acid, I had 0.5 molar, and that was times 0.5 liters. Now I'm adding, because I'm adding acid, 1 times 0.01 over 0.51 liters. So I can get rid of the 0.51 liters. So what I really have is my pH is equal to 3.74 plus the log of 0.7 times 0.5 minus 1 times 0.01 over 0.5 times 0.5 plus 1 times 0.01. And when I do all this out, I get a pH equal to 3.856, which is close enough to a pH equal to 3.86. So you can see that there really was not much change, 3.89, okay? So a buffer resists a pH change. So my pH before in my buffer system was 3.89, and now I added a strong acid, and it really didn't change much, okay? It went 3.86. So you have to solve for the buffer system first, and then figure out, now if we were adding a base, then I would have been increasing, this would have been a plus up here and minus on the bottom. But what happened was I added an acid, and when you increase the acid, it collides more with the base, decreasing the base, producing more of the acid and the OH. All right, let's get to today's problems. Adding strong acids and bases to solutions. Equa means equal. So our equivalence point is when the moles of H plus equal the moles of H minus. How do you know when you've reached the equivalence point? Well, one way is the use of an indicator. Actually, there's two. The first one that's probably the most that you're familiar with is the phenolphthalein. And that you have acid base, this would be colorless to pink. Another one that you can use is bromthymol blue. This goes from yellow in an acid to blue in a base. And the other way is using a pH meter and graphing it. And the intersection of the steep slant is the equivalence point. So here's the graph, and here's my steep section. Here is the intersection of that, which on this graph, whoa, you can see should be around a pH of 7. And that's what you'd be looking for on your graph. So let's do some practice problems. We've got about 8 to go through. So in this first one, we are adding a strong acid and the salt of a weak base. We have 20 mils of 0.25 HCl. That's a strong acid. So it's NaNO2, sodium nitrite. We're not interested in the Na. The NO2 minus is the conjugate base of a weak acid. And that weak acid would be HNO2, nitrous acid. Remember that you always need an acid and base, and two partners must be on opposite sides when you're writing your equation. I'm getting my H from the HCl, my NO2 minus from my conjugate base, and I am forming HNO2. Here's my acid and here's my conjugate base. They're on opposite sides. We're going to see what we have initially. We have 20 times 0.25 for my acid, which is going to give me 5. My NO2, I have 7. 20 times 0.35 is 7, and I have none of this initially. That as the reaction takes place, that I'm going to use up all of this first. So -5, -5, +5. And I'm going to be left with 2 and 5. And this is 0. So you can call this an ice table, initial, change, and at equilibrium. Notice here that we have partners, NO2, HNO2, and we have significant quantities. Therefore, we can use Henderson Hasselbalch. We just need to know the Ka for HNO2, which if we look up in A23 is 4 times 10 to the -4. So pH is equal to the pKa plus the log of the base over the acid. So my pH, the negative log of 4 times 10 to the -4 is going to be 3.4 plus the log of my base, which we said is 2 over 5. And that's going to give me a pH equal to 3.00. Let's move to the next one. Example 5, I have a strong acid and a buffer solution. So what is the pH when 15 mils of nitric, there's my strong acid, is added to a buffer that contains 50 mils of 0.25 molar HCO2H and 0.3 molar NaCO2H. The easiest way to really see what's going on here is to imagine a beaker. And this to me is the easiest way that I found to understand buffers. Unfortunately, students don't always want to do this, but I am encouraging it. So in my beaker, I have HNO3, which is strong. It's a strong acid, right? And that's going to dissociate into H plus and NO3 minus. Also in my beaker, I have HCO2H, which is formic acid, which is a weak acid. Therefore, in the presence of this, probably will not dissociate. And I have sodium formate, NaCO2H, which is the salt of a weak base. What's going to happen is this is going to dissociate in solution, and more than likely this is going to combine with this, and it's going to make that. So you've got H plus CO2H minus yielding HCO2H. Couple of things. You have an acid-base pair right here, the formate ion and the formic acid, and they're on opposite sides. So we're going to need the Ka of formic acid, which we looked up earlier, was 1.8 times 10 to the minus 4. So we're starting with 15 mils of 0.2, which is going to give us a concentration of 3 for our hydrogen. We've got 50 mils of 0.25 molar formic acid. So 50 times 0.25 is going to be 12.5. And we have 50 mils of 0.3 of the sodium formate, which is the formate ion, which is going to give us 15. So as this reaction proceeds, you can see that the H is the limiting reagent. And I'm going to wind up with 0, 12, and 15.5. So we have an acid-base pair right here, and we have significant quantities. So we can do our pH is equal to our pKa plus the log of the base over the acid. So the pH is equal to the negative log of 1.8 times 10 to the negative 4, which is going to give us 3.74, plus the log of our base, which is 12, over 15.5, which is our acid. And when we solve for pH, we get 3.63. Okay, example 6, a strong base now and a buffer solution. We have 15 mils of sodium hydroxide and a buffer that's 50 mils of 0.25 molar formic acid and 0.3 molar sodium formate. So we're using some of the stuff that we just used. It'll make it easier. Let's look at our beaker again and see what's in there. I've got NaOH, which is a strong base. So that's going to dissociate. I've got my weak acid, which is going to stay intact. It's my weak acid. And I have, again, my sodium formate, which is the salt of a weak base, and that's going to dissociate into Na plus and CO2H minus. So what's going to happen here, my acid is going to react with my base. Remember my original equation that I showed you earlier, Hx plus base is going to yield, do you remember? X minus and H2O. So this is when I add base. Okay. So I take my acid, HCO2H, and I add my base, and I'm going to get CO2H minus, because this H comes over here to form water. Now we're not interested in the water. We need our initial concentrations. The acid was 50 times 0.25, which gives us 12.5. Our base was 15 times 0.2, which gives us 3. And our formate ion was 50 times 0.3, which was 15. So here my base is going to get used up, and this is going to become 9.5, 0, and 18. I have an acid-base pair, acid conjugate base. I have significant quantities. So my pH equals the pKa plus the log of the base over the acid. Well, we just figured out the pKa was 3.74 plus the log of the base, which is 18 over 9.5. And that's going to give me a pH equal to 4.02. I just want to show you that you can still do this the other way. You can still do this. Let's say I'm just gonna do it over here in the corner, just so you can have a point of reference. So I've got my HCO2H, and that dissociates into H plus COH2 minus. Initially, right, I had 9.5 of this, but when I do an actual ice table, I need molarities. So this would have to be over the total volume, which is 65 milliliters. My H is 0, and my base was 18 over 65 milliliters. So this is going to be minus X plus X plus X. This winds up being 9.5 divided by 65 is 0.146 minus X. This is X, and this is going to be 0.277 plus X. Ka is going to be equal to 1.8 times 10 to the minus 4 equal to 2.277 plus X times X over 0.146 minus X. And in solving for X, in my solver, I get 9.48 times 10 to the minus 4. That's going to give me a pH equal to 4.02. So you can see that I actually come out with the same answer, but it's a lot easier doing it this way. Now, one point of clarification. I know that I use an ice table here, and I tell you that you need to use molarities. I still label this an ice table, but this is where I'm telling you that a lot of people label this before, change, after. A BCA table. I called it a BAC table before. And it's not. It's a BCA table. I don't know. Maybe you don't want to label your table. I'm not sure how to address that with you. But technically, if you're using an ice table, it has to be in molarities. If you're using a before, change, after table, then you can have it in millimoles, which is kind of what we're doing here. Okay. Moving on to example 7, a strong base and a weak buffer solution system. What is the pH when 40 mils of 0.25 molar NaOH is added to a buffer that contains 100 mils of 0.4 ethylamine and 0.4 ethylammonium chloride? Again, I like to use the beaker system, see what's going on. I've got Na plus in here and OH minus. That's going to dissociate. I'm going to have a weak base, which is going to stay together, C2H5NH2. It's a weak base. And ethylammonium chloride, I'm going to have the Cl ion in here, which I'm not interested in. And then I'm going to have the C2H5NH3 plus ion. So again, your base is going to mix with your weak acid and form the ethylamine. So we've got C2H5NH3 plus OH minus is going to yield C2H5NH2 and water. Couple of things going on here. I can find the Kb for this. So the Kb for the the ethylamine is going to be 5.6 times 10 to the minus 4. I can get that from the back of the book. However, I'm going to need the Ka because you're going to see that we're going to be able to use Henderson Hasselbalch here. So I'm going to do that over here now. Ka equals Kw divided by Kb. So our Ka is going to be equal to 1.79 times 10 to the minus 11. Now so we look at our changes. I'll label this and I'll put the ice out here. So beforehand I've got 40 times 0.25, which is going to give me 10 millimoles here. And I've got C2H5 and H3, which is going to be 100 times 0.4, which is going to be 40. And I also have C2H5 and H2 is also going to be 40. So this is going to be minus 10, plus 10. At the afterwards, after it's added, this is going to be 30, 0, and 50. So I have significant quantities of an acid-base pair. Here's my base. Here's my conjugate acid. So I can use Henderson Hasselbalch. So I've got pH equals the pKa of 1.79 times 10 to the negative 11 is going to be 10.75. Just take the negative log of your Ka plus the log of your base, which is 50 over 30. And I get a pH equal to 10.97. Let's move on. A strong base and a weak acid. What is the pH when 40 mils of 0.25 molar NaOH is mixed with 20 mils of propanoic acid? In my beaker, basically real easy, NaOH minus, and propanoic is a weak acid, HC3H5O2. So these two are going to combine. So we've got HC3H5O2 plus OH minus is going to yield me the propanoate ion, C3H5O2 minus, and water. Before, change, after. You can only use this if we're using true molarities. We're using millimoles here. I've got 40 times 0.25, which is going to give me 10 millimoles for the base. 20 times 0.5 is going to give me 10 millimoles for the acid. This is 0. So this is going to be minus 10, and this is going to be 10. So 0 and 0 and 10. So I know that I don't have an acid-base pair here. Therefore, I can't use Henderson Hasselbalch, which means that I'm going to have to do this the old-fashioned way. So the first thing I need to know is the Ka of my acid. Well, we've got to get this back so that we actually have an acid. So we're starting with our ion. I'm going to put this right below it. C3H5O2 minus plus H2O is going to yield HC3H5O2 minus plus OH minus. So now we have to do an ice table. We need true molarities. So we have 10, which we just figured out was what was left afterwards. Our total volume is 40 plus 20, so it's going to be 10 divided by 60, which is going to be equal to 0.167. We don't have to worry about water. This is going to be minus x, 0.167 minus x. This initially is going to be 0, plus x, x, and x. Now, I can find the Ka of this, but what I really am finding is the OH minus. So I'm going to have to find the Ka and use that to find the Kb. So our propanoic acid, the Ka is equal to 1.3 times 10 to the minus 5. So Kb equals Kw divided by Ka. So therefore my Kb is equal to 7.69 times 10 to the minus 12. So now we're back to our old method. We've got Kb equals 7.69 times 10 to the minus 12 equal to x squared over 0.167 minus x. In my solver, I'm going to get x, which is equal to my OH minus concentration, equal to 1.13 times 10 to the minus 5 molar. From that, I can find my POH by doing the negative log of my OH concentration, and that's going to give me 4.94. And then I can subtract that from 14 and get a pH of 9.05. And that's my end on this one. So I had to wind up doing an ice table afterwards because there was only one concentration left, and I didn't have an acid-base pair present in significant quantities to use Henderson Hasselbalch. In 9, I've got a strong base and a weak acid. So again, I've got NaOH, and that's mixed with propanoic acid. I'm using the same thing, just changing it up a little. I'm not interested in the Na, so it's simply going to be HC3H5O2 plus OH minus yields C3H5O2 minus plus H2O. BCA before, I've got my base 42 times 0.25, which is going to give me 10.5 millimoles. And my acid, I've got 20 times 0.5, which is going to give me 10 millimoles. And this is 0. So it's going to be minus 10, plus 10. It's going to be 0. It's going to be 0.5. And this is going to be 10. And we don't care about this. So what we have to remember here is strong versus weak. Strong always wins. So I don't have to do anything because all I know is that the concentration of my OH minus is going to be equal to molarity equals moles over liters. So I've got millimoles here, 0.5 millimoles over a total of 20, 42, 62 milliliters is going to give me a total of 0.5 divided by 62 is 0.008 molar. And then I can just take the negative log of that. So my POH is going to be equal to the negative log of that, which is 2.09. Therefore, my pH is going to be equal to 11.9. This was actually 2.09, and this is actually 11.91, sorry, so that we're accurate, and everything adds up to 14. Okay, 3 more to go. Actually, I think there's 4 more. I numbered one twice. All right, Strong acid, weak base. Strong acid, weak base. We've got 20 mils of 0.2 molar methylamine mixed with 10 mils of HNO3. So we're interested in what? We're interested in the H from the HNO3 mixing with the methylamine. So H plus my weak base, CH3 NH2, is going to yield CH3 NH3 plus. Let's look at what we have. Before, we've got 20 times 0.2 of the methylamine, which is going to give me 4, and I've got 10 times 0.2, which is 2 of the acid, and this is 0. Minus 2, minus 2, plus 2, 0, 2, and 2. Well, here it should be pretty intuitive. Here's my acid-base pair, okay? And the log of 2 over 2 is simply going to be 1. So in this case, my pH is simply going to equal my pKa. So we need to know the Kb of the CH3NH2. So Kb of CH3NH2 is equal to 4.38 times 10 to the negative 4. So in this problem, we have the Kb of CH3NH2, which is 4.38, so we need the Ka, so Kw divided by Kb. So our Ka is going to be equal to 2.28 times 10 to the minus 11. So pH equals pKa, and our pKa is equal to, so that's the negative of the Ka, which is 10.64. That's our answer. Pretty easy on that one. Strong acid, weak base. Didn't we just do that? Oh, we did. Yeah, we just did a strong acid, weak base. So this is a different one. Here again, let's see. We've got the strong acid. We're interested in the H, so this is going to be H plus the methylamine, CH3 NH2, and that's going to form CH3 NH3 plus. Let's look at what we have. I think we're starting with the same numbers. 20 times 0.2 is going to give me 4 on this. 20 times 0.2 is 4 on this. 0, I can see what's happening here. What's happening? 4, 4, 4, 0, 0, 4. Again, we cannot use Henderson Hasselbalch because we only have one substance. So we have to do an ice table. So we're going to have CH3 NH3 plus, and we need to add water to this, HOH or H2O, and we're going to get CH3 NH2 plus, oops, no plus, NH2 and H3O plus. This is a base, and we need to find the acid. So again, I'm not going to redo the work. We just did this. We found the Ka using the Kb of the methylamine. So our Ka is the same in this problem. Ka is going to be 2.28 times 10 to the minus 11. ICE, remember we need concentrations. So now we have to put it over the total volume. We've got 4 divided by 40, which gives us 0.1. So 0.1, we're not worried about water, and we've got 0, 0, minus x, 0.1 minus x, plus x, plus x, x, and x. So Ka equals 2.28 times 10 to the minus 11 equal to x squared over 0.1 minus x. Using our solver, we solve for x, and we get x, which is equal to H3O plus, equal to 1.5 times 10 to the minus 6. So our pH is equal to the negative log of that, and our pH is going to be equal to 5.82, which is a weak acid. And that should make sense intuitively, because if I have a strong acid and a weak base, I'm going to be left with a slightly acidic solution. Okay, we need to change this to number 12, because I labeled two of them 11. So this is going to be 12, and this is going to be 13, and then we will call it a day. So now I've got another different type of problem with a strong acid and a weak base. Slightly different. I'm still using the H from the HNO3 plus the methylamine, which is the base, to form CH3 NH3 plus. I'm starting with 20 times 0.2, which is 4, and 24 times 0.2. Oh, that was my acid, so this is 4.8. Sorry. 24 times 0.2 is 4.8. My base is my 20 times 0.2, which is 4. This is going to be 0. My change is going to be minus 4, plus 4, and afterwards I'm going to have 0.8, 0, and 4. Again, I have a strong acid versus a weak base. Strong versus weak. Strong wins every time. Therefore, I can just calculate the concentration of my hydrogen ion, which is going to be 0.8. This is millimoles, remember, over my total volume. 20 and 24 is 44 milliliters, which is going to give me 0.018 molarity. And then my pH is equal to the negative log of my H concentration, which is going to be equal to 1.74. If we compare, so in this problem, I had no buffers because there were no partners. And this last problem, this is always, whenever you see a ratio problem, that's always your hint that it's going to be Henderson Hasselbalch equation. So you know right away you're going to be using the pH is equal to the pKa plus the log of the base over the acid. So what we have here is NH3, NH4, and you need to find the pH. So what we can find is we can find the Kb of NH3, which is equal to 1.8 times 10 to the minus 5. We can look that up. And then we can find the Ka by taking the Kw and dividing it by the Kb, and that's going to give us 5.56 times 10 to the minus 9, I believe. Let me just double check that. So taking the Kw, dividing it by the Kb will give us a Ka of 5.56 times 10 to the minus 10. And then we need to take the negative log of that, and that's going to give us 9.255. So that's going to give us a pKa equal to 9.26. So going back up here, we've got pH is equal to 9.26 plus the log of the base. Now you have to look at, be careful how they give this to you in the problem. Here it's the ratio of NH3, which is our base, to NH4 plus, which is our acid. So they've given us the ratio base to acid. However, it could be written acid to base in the problem, which means that you would have to invert the ratio. So that's going to give you a pH of 9.76. And that is the end. That's all, folks. All right, next lesson will be on acid-base indicators and titration curves.